welcome back to operating systems. It's midterms probably for the rest of your courses, so yay. So today we're doing another scheduling example just because it's like it's like 20 minutes or something, didn't quite fit in scheduling. Then after that, we're just doing something that is good to know, but you don't have to know it for our exam, which is like also in like a month anyways. So yay, reading week at weird times. So anyways, let's get into it. So we'll explore an example of dynamic priority scheduling. Might also be called in some literature feedback scheduling. So it's just an algorithm to manage the priorities for you. All you set is an initial priority for the processes and then let the algorithm take over. So it uses set time slices, measures CPU usage, and then tries to adjust the priorities dynamically. Based off that, we'll see the algorithm that they use. It's not terribly complicated as long as we know how to divide by 2. So the idea behind it is we increase the priority of processes that don't use their time slice, so they haven't been scheduled. So we want to make that number lower, and we want to decrease the priority of processes that use their full time slice and make that number higher. And the idea behind this is hopefully if you haven't run in a while, you will have a higher priority until you finally run. We try and be fair and all that, but we allow you to set a initial priority so that some processes definitely get scheduled before others. So, like I said before, we pick the lowest number. That means the highest priority, same as in Linux priorities. So, initially, when a process starts, it gets assigned some priority, call it P of n, and then whenever we schedule, we pick the lowest priority to schedule. If it yields, we pick the next lowest number. If there is a tie of the same priority, we break the ties with the arrival order. And if something, this is going to be preemptive as well, so if something with a lower priority number is able to execute again, we will context switch directly to it. So for this, we record how much time each process executes for its priority interval, which might be the same distance as a time slice, but typically you don't recalculate priorities every single time you do a context switch. You do it every so often at a fixed priority because it's essentially some extra work you have to do. So you record how much time a process uses during its interval. That is called C of n. And in this, timer interrupts still occur, so we can have preemption. So our calculation is at the end of the priority interval. We update the priority of each process with this formula. So it's P of n, so its new priority is equal to its old priority divided by 2. So it gets lower and lower, which means we are more likely to execute it. And then plus however long it executed for that time slice. So if you just executed, your number will be higher, you will have a lower priority, and it is more unlikely that you will run. And each time we go through we reset the priority interval, we reset our counter of all the processes back to 0. So what's that look like? So let's assume we have 4 processes, X, Y, A, and B, and they are in that arrival order. So X, Y, A, and B, they all have an initial priority of 0. So that is the initial priority we'll work with all processes. So initially they're all tied. So we'll go with arrival order. So A and B are CPU-bound processes. What does that mean? It means whenever they're ready all the time, they just want to execute CPU. They don't block or anything. They just want to execute on the CPU, doing some important or not so important calculation. X and Y are IO-bound processes, so they execute for 1 time unit, and then they block for 5. So that means they cannot execute. They're waiting on a file. They're doing something. They're blocked. They can't execute for 5 time units after they execute. So we'll have the opportunity to schedule other processes. So in this, timer interrupts recur every 1 time unit, so we could context switch then if we wanted, get control back to the kernel. And here each time slice is 10 time units, so that's the maximum amount of time any process can be scheduled for. And our priority interval is also 10. Typically, these are the same thing. I separated out because the time slice is like a maximum. The priority interval happens every 10 time units. So in this case, what is the scheduling where we could preempt at any single time unit? Well, initially, they all have the same priority. They're all 0. They're all of the same priority level, so we go by arrival order. In this case, X comes first. It executes for 1 time unit, and then it's done. So since it's done at time equals 1 and blocks for 5, we can't execute it again until 6 time units. So next highest runnable priority is Y because it arrived after X. So it would also execute for 1 time unit, and then it would also block for 5. So we can't execute Y again until 7. So now we can only schedule between A and B. A came first, so we'd schedule A. So A would be available or would execute all the way to time equals 10 whenever we have to recalculate priorities. Why? Well, X became ready at time 6, but it didn't have a higher priority, so we wouldn't bother to switch to it if we're already running something of equal priority. Similarly, at time 7, Y was ready, but we didn't switch to it immediately because our priorities were tied. So at time 10, we recalculate our priorities. So priority of process X is, well, it's old priority. They all started at 0, so this term's just going to be 0 for all of them. So plus however many time units they executed for in the last 10. So X executed for 1, Y executed for 1, A executed for 8, and B executed for 0. So those are our new priorities. So at time 10, well, we have a process that has a lower priority, or it is a higher priority, or a lower priority number, or a higher priority than the rest of the processes. So at time 10, we should switch to process B because its priority is the lower number, highest priority. So we would switch to B for the next 10 time units, and then we'd recalculate the priorities again, and hopefully this isn't terribly complicated. So any questions about that? No? Pretty straightforward. All right. So same thing, except now A and B have a priority of 6. So that is a higher number or lower priority. So we would prefer to execute X and Y over A and B. So in this case, going to start the same. There's a tie between X and Y. Their priority is 0. So X arrived first, so we pick X. So it runs for 1 time unit, blocks for 5. Execute Y, runs for 1 time unit, then blocks for 5. Now, in this case, we don't have any processes that are of priority 0, so our next priority is 6, and we have a tie between A and B. A came before B, so we would schedule A for 4 time units. Now at time 6, well, X is ready again. So if X is ready again, it has a lower number or higher priority, so we would switch directly to X. It would execute for 1 time unit, then block for 5. Y does the same thing, executes for 1 time unit, blocks for 5. And then we're back between A and B, and we would choose A again until time 10, whenever we have to recalculate the priorities. So in this case, when we recalculate the priorities, the priority for X and Y were initially 0, so 0 divided by anything is still 0, and both of them ran for 2 time units, so their new priorities are both 2. Process A, well, its old priority was 6, or its initial priority was 6, so we divide that by 2, and it ran for 6 time units, so 6 divided 2 is 3 plus 6 equals 9. So its new priority is 9. Then process B, well, 6 divided 2, it ran for 0 time units. Its new priority is 3. So in this case, X and Y still have a lower priority number or higher priority, so they'll execute again whenever they're ready. But in this case, we would switch to process B for 2 time units. It would execute to time 12. until X is unblocked. Then whenever X is unblocked, runs for 1, gets blocked again, Y executes for 1, gets blocked again, switch back for B for 4 time units, then X is unblocked, so we can schedule it again, and then Y, and then we're done. Yay! Any questions about that? Yep.
Why do you choose to run a complete A instead of switching to B at time A?
At time when, sorry?
At time A,
So at time 8, we haven't recalculated the priorities at all. So A and B are still tied, and A arrived first. So we go back to A. And then at 8, Y, okay. Yeah, so in this case, both their priority was 6 at that point. So we go by arrival order, and A arrived before B. So we pick A. And it's the same reason we picked A at why we picked A at time 2 is the same reason we picked A at time 8. We haven't recalculated the priorities yet. Everything's the same. All right, any other questions? Yeah.
Let me ask the time 8, like the A has already run for 4 time slices, but the B has not run for any time slices. Why choose A at the time 8?
So in this case, we haven't at time 8, we haven't recalculated the priorities yet. We only recalculate them at time 10. So at time 2, whenever we scheduled A then, A and B were tied in priority, and A arrived first, so we picked A. So at time 8, we didn't recalculate the priorities. We can only run A and B. They're tied for priority, so we went to arrival order. A came first. All right. Good, pretty boring. That's the new content for today. Yay. All right. Other fun stuff that you don't have to know for the exam, but you may want to appear as a wizard, especially in machine learning courses. So, large language models are huge, 30 billion parameters or something like that. They take like 20 gigs of memory just loading the contents of the file. So, someone wrote a program that uses a large language model, and someone did a single line of change before. That thing needed to read like a 20 gig file in the memory, took up 20 gigs of RAM at least, so you had to have 32 gigs of RAM to even run this thing. Then someone did a one line change, and suddenly it only took 6.8 gigs of RAM. So how is that possible? So there's a whole discussion about that, and we will see the magic behind it. It was like a one line change. Well, a few more, like 5 lines. But in order to get into how that worked, well, we need to learn about Nmap, so we can actually control our process's virtual memory. So there is a memory map system call, or Mmap, and that allows us to do fun things like map files to virtual memory addresses. And then if we do this, we just have a pointer, and you can access the file directly as if it was memory. There's no need for read and write system calls. There's no need for buffers. There's no need for anything. You just use it as if it is one big array of bytes, and it is quite awesome. So let's just dive into the example and see it. And this is like how most programs deal with files, because 1, it's way more efficient, and 2, it's actually less lines of code. So you just have to know how virtual memory works in order for this to make sense at all. So at the beginning, we just open a file. We will just open this own source code file just to be a bit meta. So we open it as read only. We get a file descriptor. Yay, it's the same thing. We could have just done a read system, create a buffer, done a read system call on this, and printed it out to standard output if we really wanted to, but we can do something more fun. So there's this other system call that is not really covered in the course, but might be useful. So there is the stat struct, which tells you lots of information about files. Basically, it tells you all the information. If you do an ls and see like this line, you see like permissions, a number, we will figure out what that means later, who owns it, what group owns it, how big it is, the date it was modified, and all that. Well, that information is all stored in this struct called a stat struct, and you can do a system call to populate it and ask the kernel to give me some information about this file. So we do an fstat system call with fd, which should be a file descriptor pointing to that mmap file, and then we give an address so it can fill in the fields for us. And then we're only really concerned about the size, so there's a field called stsize in the stat struct that just tells you how big the file is. So after we figure out how big the file, we do an mmap system call. So it has 6 arguments, and we will go through them one by one. So the first argument is the address. So you are allowed to specify whatever virtual address you want if you are picky about a virtual address and for some reason you want a set address. So if you don't care what virtual address you get out of this, you can just set that to null and let the kernel decide. So 99% of the time that will always be null. Next argument is the length. So how much virtual memory should it set aside for you? In this case, I ask for the exact size of the file because I want this block of virtual memory to represent the file. Next is protection. So those are permissions, which kind of correspond to the same permissions as your page table entry in Lab 3. So you can say, hey, I want to read, just read this memory, and then if I try and write to it, I'll get an error. If I wanted to write to it, I could just enable that flag, and so on and so forth. The next one is a fun flag. So this flag specifies what happens when a fork happens. So this flag right now says map private. So that means for each process, if you fork, it's going to behave like fork normally behaves, in which case your own virtual memory space is yours. It's independent. If one process changes it, it doesn't change it in the other. That's what we know and love. If you wanted to, you could change this to be shared, in which case it will map to the same physical memory, and if you change it in one process, you change it in the other one. So this is also a way to do IPC if you want. You can just set up some virtual memory, have it shared, and then whenever you fork, that virtual memory maps to the same physical memory. So if you change it in one, the other sees it. All right. Next argument is the file descriptor. So if you want it to represent a file, what file do you want it to represent? In this case, we just give it FD. And then offset is how many bytes into the file should I start this mapping. If we want to read the whole file, our offset is 0. So in this case, we check to see if it failed or not. Then we can close the file descriptor because we don't need it anymore. We will access this file through that virtual memory. So now I can just write a for loop that iterates over every single byte in the file, and I'll just do a printf, and this data now, this array of data just corresponds to the contents of the file now. So data at 0 is the first byte of the file, and I could go to the last byte of the file. I could read any part of the file at any given time. Don't have to do any read or write system calls, don't have to screw with buffers, don't have to worry about everything, and the nice thing is this is also more efficient. So also, whenever we're done with it, like you have malloc and free, when you have mmap, you should free it with an munmap system call, and you also have to tell it the length. All right, cool. So if we execute that, or if we build that and execute it, hey, guess what? We read out the contents of the file. No fuss, no muss, no buffers, no anything. Kind of cool. At least I think it is. And most programs that want to be efficient, they don't use fopen, they don't use anything like that. They use mmap because it's way better. So, any questions about that? All right, so let's discuss quickly how it kind of works. So mmap is really lazy. All it does is set up page tables. It doesn't actually read anything from the file. So what it would do is create kind of set aside page table entries, as many as it needs. So it would set aside however many pages it needs to fit in that mapping, and it would create invalid page table entries during that mmap call and kind of reserve some virtual address space. Now, because of this, if the MMU tried to resolve this, it would page fault because they would be invalid. So the kernel can go ahead and use the rest of the bits for whatever it wants, all 64 of them. So it would actually use the rest of the entry to have some bookkeeping information saying, hey, what does this entry represent? What file does it represent? And where in the file does it represent? So whenever you first access that memory, it would do a page fault, and then the kernel would see, oh, you have an invalid memory. It should be mapped to this file. Then it would read that file into memory and replace it for that address, so it would just do it lazy. So you only will load what parts of the file you actually use, which is really hard to do if you don't have mmap. If you have to, jump around the file, make sure your buffer's the right size, it's just a real pain in the ass. You can just have the kernel manage it for you, and this ensures that only the parts of the file you use actually get read and put into memory. So it's only pay for what you use. Just let the kernel do all the hard work. So if you go into the discussion, someone says, oh yeah, all I did was mmap it, because large language models, usually whenever you do inference, you do not use all of the model to do a single inference. You only use parts of the model. So all it does is mmap that 20 gig file, and that's it. It just reads from it, whatever parts of the model it reads from. Let the kernel figure it out, read it into memory. In this case, it only uses a few gigabytes instead of the entire file. And it's great, super efficient. They were like, wow, you were a wizard. How did you make this? Suddenly you cut the memory usage down by 2/4. Wow, you should definitely take an operating system course. So then later on in the discussion, they were like, oh yeah, well, how much space does the kernel actually need for page tables? Isn't this super wasteful to do a whole 20 gigabyte file? Well, someone posted in that you only need 20 megabytes of page table entries. So in this case, how they came up with that number was 20 times 1024 times 1024 times 1024. So this is just 1 gigabyte, or 2 to the power of 30, which is a real gigabyte. And then they figured out, well, if you have 20 gigabytes of memory, how many pages do you need? And this number, again, our favorite number, represents a page size. So that is how many virtual pages I actually need to map this file. And then they multiplied it by 8 because each of those virtual page numbers needs a page table entry. So our page table entry is 8 bytes. And then they just divided by 1024 times 1024, which is 2 to the 20, or a real megabyte, in order to get the answer in megabytes. So someone clarified later that this was 20 gigabytes, so this part divided by the 4K page size, which is that, times the 8 bytes per page table entry divided by 1 kilobyte, which must have been a typo because they meant 1 megabyte. So is this correct? Is this the only thing we need for the page tables? Yeah.
You also need multiple levels for the page tables, right?
Yeah, so this has multiple levels. So that number represents how many entries you would need in L0, but we have different levels. So we could, if we wanted to be super pedantic, we could calculate how many L1 tables we need for this and figure out how many of the L0 page tables would actually be full in the best case. So this is like super, like actually I want to be like correct. So you will impress no one at a party if you know how to do this. I don't know why this is here. This is mostly here so that we can understand like, hey, multi-level page tables. So in actuality, well, yeah, we need 20 gigabytes of space, and each page is 2 to the 12. So we need 20 times 2 to the 18 page table entries. So those, again, are only for L0 page tables. So we can take the number of page table entries and divide it by the number of page table entries we can fit in each table. So this is 2 to the 9 because we only have 9 bits to figure out each index on a page table with our systems. So if I just do the math on this, it just becomes 20 times 2 to the 9. And if I write out the answer, that means we have 10,240 full L0 page tables in the best case. So that's the best case where all of them are full. In this case, all the addresses are going to be contiguous anyways, so all the entries are going to be beside each other. So our worst case is like the first table might not be completely full, which would make the last table also not full. So we might, in the worst case, this would be 41, and that's also super pedantic. So we can just assume best case here, we would have 10,240 full L0 page tables. So we know each L1 page table can point to up to 512 L0 page tables for the same reason, right? That's how many entries it can have in it. So if we just take the 10,240, divide by 512, well, we can figure out that we need 20 full L1 page tables in the best case. So in total, we need 1,240 L0 page tables, 20 L1 page tables, so we would need 10,260 full tables. In this case, we wouldn't add an L2 page table because each process only has one of them. It would already have one. It would already have entries in it already. So in this case, if we figure out this number, we multiply by the size of a page table, so 4,096 again, then divide by megabytes. We get, actually, it took 40.07 megabytes, not 40. So slightly more. Again, I don't know why I did this. All right, any questions? Because that was pretty much it. All right, cool. Work on lab 3 or study for other midterms, I guess, because you will probably do that. All right, just remember, pulling for you. We're all in this together.